So let's look at a couple of examples applying the central limit theorem. The first one is example 5.3 from the textbook. Using the central limit theorem, compute the mean and standard error of the sampling distribution of sample proportions when the population proportion is 88 hundredths or 88% and the sample size is 1000. So the solution in this case, the mean of the p hats is simply the population proportion that comes directly from the central limit theorem formula. And the standard error of p hat uses the formula that the standard error subscript p hat is equal to the square root of p times 1 minus p over n. And I've shown the numerical calculations for that, where I got a value of 10 thousandths. All right, the second example from our textbook, I want to estimate how frequently the sample proportion p hat should be within 2% of the population value of p equals 88 hundredths. Well, because the conditions for the central limit theorem are met, that is independence and the success failure conditions, we can see example 5.2 in our book to see that those are both true. We know that the sampling distribution of p hats is approximately normal with a mean value of 88 hundredths and a standard error of 10 thousandths. And therefore, we can draw a normal distribution sketch to answer this question. So let's go ahead and do that. Here's a normal distribution sketch. Notice that I've labeled the variable axis as p hat. We're scaling the axis by units of standard error in this case. Remember, our standard error was 10 thousandths. So I went up 3 standard errors and I went down 3 standard errors from this value in the center of 88 hundredths. Okay, so now that we've gone ahead and scaled our normal distribution sketch, I would draw vertical lines through 0.86 and 0.90. Notice that those values are 2% below and 2% above the center value of 88%, which was what we were given in the problem statement. And then I would label down below the z-score values corresponding to those two values, which are -2 and +2. And then up above, I would label those variable values of 86% or 86 hundredths and 90% or 90 hundredths. And notice what we're looking for is we're looking for the area under the curve between those vertical lines. Now, normally, if I were drawing this on paper, I would have shaded that particular region. And then now we need to go find what that probability is. And we're going to use our guru to do so. So let me go ahead and go to our guru and find that probability value. All right, so here we are in our guru. I'm using the continuous distributions probability calculator for a normal distribution with a mean of 0, standard deviation of 1, and I'm looking between -2 and 2 for my z-score values, and the probability of that happening is 0.9545 or approximately 95%. So looking back at the original question we were again asked to estimate how frequently the sample proportion p hat should be within 2%. We now know the answer to that is approximately 95%. Let me go back through the to my one last comment that I want to make. Sorry about that. There we go. All right, one last comment. Suppose we do not actually know the population proportion, as we have assumed throughout today's scenario. What do we do in that case if we don't know the actual population proportion for being able to apply the central limit theorem, in other words? Well, what we do is this. We assume that our earlier value of p equals 88% was based on a Pew Research conducted poll of 1,000 American adults that found that p hat was 887 thousandths of them favoring the expansion of solar energy. The researchers may have wondered, does the sample proportion from the poll approximately follow a normal distribution? Well, we can check the conditions from the central limit theorem. Independence is definitely going to hold because it was a simple random sample of American adults. That means the observations are independent. But here's where things break down because we only have a sample proportion. To check the success failure condition, we need the population proportion p. However, we don't actually know p, which is exactly why the pollsters would take a sample. So what do? Well, in a case like that, we often use the sample proportion p hat as our next best way to check the success failure condition. So in that case, we simply find the number of successes, which would in this case be 887, using p hat as an estimate for the population proportion, which we don't know, and then the number of failures would of course be 113. Notice that those two values, 887 and 113, have to add up to the total number of participants in the sample, which was 1,000. So the sample proportion p hat acts as a reasonable substitute for the population proportion p during this check, and each value in this case is well above the minimum of 10. This substitution approximation of using p hat in place of p is also useful when computing the standard error of the sample proportions. And that concludes this presentation.